All right, forces on wires, and we're going to also talk about forces on charges. So they're going to be kind of grouped together. So you saw the demos, little wires jumping, that's how we get to a motor. And the motor parts will be discussed when we do the generator because they're the same parts. But you saw what they were. So basically, when we know current flows in a conductor, you're near a magnet. Remember, that creates its own magnetic field. It interacts with this magnetic field, and it experiences a force. Force equals the field times the current times the length. Bill. It happens when the forces and the fields are at 90 degrees. If they are parallel, okay, nothing happens. If F and B are parallel, nothing happens, there'll be no force. All right, so let's do a couple problems. What force is exerted on a wire at right angles or perpendicular? That's just putting it in to know that you can use the formula. So I have current, 2 amps, field strength, 2 Tesla, and the affected length is going to be 0.02 meters, right? We're always going to convert. F equals BIL, so we're going to have 2. Sorry, did I write one down wrong? 3 Tesla, my bad. Times 2 times 0.02. All right, on 3 times 2 times 0.02, you can probably do that in your head. Okay, 0.112 newtons. So what's really going on inside wires? It's electrons, it's charges moving. So I want you to think of it like this. Force equals BIL. Well, the definition of current, back from electricity, I equals Q over T. So I'm going to substitute that in there. So I'm going to have F equals B, Q, L, and I'm going to put T in here. Well, L over T, you might as well have distance over time, is the definition of velocity. So F equals B, I'll use lowercase q most times, and V. V is the velocity. Now, a lot of times I'll do a shortcut, and I'll do BeV, because many times it's an electron, and it's 1.6 times 10 to the negative 19th coulombs. That's going to be, or a proton. You're going to have that number come back. So now we're going to find the forces on individual particles, and you're going to have to remember the charge of the electron. All right, so we're going to find the force on an electron traveling 90 degrees. Again, that's just making sure you know it's not parallel and you don't get a trick question where it's 0. All right, so I have B is 5 Tesla. Oh, my speed got weird down here. Okay, V is 3 times 10 to the 6 meters per second. And the Q, or the E, is the 1.6 times 10 to the negative 19th coulombs. So F equals BQV. Oops, that's a V. So we're going to have 5, 1.6 times 10 to the negative 19, and 3 times 10 to the 6th. All right, so that's going to take a moment to do. Let's do it. All right, so 5 times 3 second EE6 times 1.6 second EE negative 19. Looks like we're getting 2.4 times 10 to the negative 12th newtons. It does. 2.4 is 10 to the negative 12 newtons. So there's going to be a new hand rule here for figuring out these directions. So rule number 2, again, if it's current, it's your right hand. If it's electrons, it's your left. Your fingers point straight to north and south. I'm usually going to just use my pointer finger. Basically, it's always going to point towards the south pole. Your thumb needs to make a 90-degree, kind of a capital L. Again, right hand, left hand. I guess I can zoom out a little bit. And your 3 fingers are going to bend. That palm, in other words, so this might be pointing south, this might be pointing up for electrons, and then my hand faces like this. Again, if it's current, it's your right hand. If it's electrons, it's your left. And now you know the physics gang signs. All right, just a joke. let's go into the picture. Here we go. So once again, I'm going to use the hand rule, but you're going to find that this can be kind of awkward because you might get yourself into some kind of twisty function, and we avoid that by simply moving the paper. So this is just a visual to show me, okay, my finger points to B, my thumb is the current, and again, if it was electrons, it would be my left hand because I have a couple of those, and then my palm, which I bend my middle fingers, not just one, because then that would be nasty. That's the direction that it would jump, just like that little wire. All right, so we're gonna do one of these at a time. I'm gonna turn them around and twist them as I need to. So unless it says electrons like these, you're going to assume it's current. First one, again, I don't look at the outside. This is the end of a wire. Electrons are going away. Remember, X means going away. So that I don't have to break my hand, I'm gonna move this. I'm gonna have my right hand. The south is on the right-hand side, so I'm pointing my finger to the right side of the page. Now this X means that the current is going away from me. I have to make my thumb point into the table or into the desk. So take your hand, lay it like this, and tip it up on the edge, and then bend your fingers. So if I zoom out, my finger is pointing to the right side of the page, my thumb is facing down, my hand is facing this way. That would be the reaction force. It would be down. Next one. Same idea. My pointer finger, again, I don't care about these two. I only care about the inner ones. It's pointing to the south. My thumb has to point the dot. That means I have current coming at me, so I put my hand like this. Keep my finger straight and bend. These guys, my palm, is going this way. All right, I'm gonna shoot over to these. Guess I'm gonna turn the paper again because these are still my right hand. These are weird because this is what the wire looked like when it jumped off the paper. We call it out of the page, or it jumped up actually. So I'll zoom in a little bit. So again, I don't really want to look at the outer parts. I'm just looking here. So I'm gonna take my fingers, because the south is on the right hand or the left hand side of the page. But this time my thumb, instead of being like on the end, I'm gonna have it flat because it's pointing the direction of the eye. So when I bend my fingers, they're actually pointing to the ground. That would mean the wire would be pressing down, and we call that into the page. Next one. Same orientation. Again, I don't care about the outer ones, I really only care about the inner ones. My finger is pointing to the left because that's where the south is, but this arrow is pointing this way, so I'm gonna have to flip my hand over like this and bend my fingers, and my fingertips right here are pointing right up at your face, which means they're pointing to the ceiling, which means it's the same as that one wire. It jumps out of the page. There's no, we just write that. We don't write anything else, no symbols. All right, so what if they are electrons? Because that's what's really going on in electron beams. Again, I don't really care about these two, so that I don't have physics yoga twister going on. I'm gonna turn the page a little bit. I'm going to point to the south, which is on the top of my paper right now, if I don't look at those. I'm gonna use my thumb to point the direction of the electrons, which is flat, because it's not an end view like these. And when I bend my fingers, they are pointing down to the page. So this would be into the page. Okay, I'm gonna do this one. Again, south is over here, so my fingers are gonna point that way. But my thumb is not pointing that electron, is it? I have to flip it, and when I bend my fingers, they're coming right up at your nose, coming straight up to the sky. That is out of the page. In other words, it would jump off the paper, just like that one wire did. All right, lots of hand rules. Shake them up. There's gonna be practice. Peace, guys.